All right, thanks a lot for the introduction. And I am Professor for Mathematics at the Bern University of Applied Sciences. And together with my colleagues, Eva Schüpbach, Urs Muntwyler, and the researchers in our group, as well as together with our industry partners, VelaSolaris and Smart Energy Link, we developed a method to predict PV energy yield for local PV plants. And after my talk, Angela Krainer will then give some comments and viewpoints of VelaSolaris as one of our industry partners. The main goal of PV energy yield prediction is for us to optimize the own consumption of owners of PV installations, which means then to get higher and more stable profit, as well as to contribute to the reduction of non-renewable energy, so to increase the percentage of PV consumption. And last but not least, these can also give contributions to the grid stability if we know what renewable energies yield in the next hours or days. So for our approach, we had two different kinds of data available. On the one hand, we have AC power recordings of, depending on the plant, but going back 20 or 25 years now. So we selected 6 Swiss PV plants that we recorded at our PVLab during the last years. And so you see on the map, the yellow marked locations are the one that we used for development of the algorithm. And we used 3 plants in a lower elevation, let's say urban areas, and 3 plants in a mountain area. For the development, we used 4 years of recorded data from 2016 to 2020. Additionally, we recorded since beginning of the year weather forecasts from 2 providers of numerical weather forecasts, namely Meteo Suisse and Meteo Blue. I need to say, unfortunately, we have not been able to get historical, means past time data before that date. So we needed to record the forecast by ourselves during the project. We recorded the parameters of global horizontal irradiation, as well as the temperature. And additionally, Meteo Blue provided us with wind parameters, humidity, and pressure. Having these 2 different data types at hand, we also chose a 2-step approach for the development of the prediction algorithm. First, we take the AC power recordings in order to model the PV plant, the basic behavior of the PV plant by Gaussian processes. So with the recorded data, we model things like inclination, orientation, efficiency of the inverter, and so on. So this describes the PV plant itself, neglecting the weather and other local fluctuations. So also with this model, we would be possible to make long time predictions and long time behavior of the PV plant. And secondly, having the results from the Gaussian process, we put this into a neural network, which then combines the actual weather forecasts together with this first prediction in order to incorporate these time local influences of the weather into the model. more precisely, you see here graphs of the two-step process. Above here on these larger graphs, you see that we have separated the AC power measurements into 3 clusters. Let's say a high-performing situation in red, a medium performance situation in green, and in blue the low performance situation, which might be compared with low weather conditions, medium and good weather conditions. So we take for every hour of the day, we take these 3 clusters and train 3 different Gaussian processes. You see the results here in the red, green, and blue lines, together with these intervals, these quantile intervals, 95% intervals. So we do that for every hour of the day, let's say for 6 o'clock and for 12 o'clock. And then the contribution of that goes into the neural network, combined with the weather forecast, which then gives us a prediction for 6 o'clock, 7 o'clock, 8 o'clock, and so on. And so we calculate predictions for a whole day. After having developed this procedure, we performed several experiments. So we asked ourselves, what is the influence of the input data, the structure of the input data we can put into the algorithm and train it. So one of our first experiments deals with the so-called temporal averaging, which means that we do not only give the actual GHI value to the algorithm, so that would correspond to the first point of this graph here. We also provide for a certain prediction the algorithm with future and past forecasting values. So we made tests with including the actual hour, a future hour, and a past hour, then 5 values, 6 values, 7 values, and so on. And so you see this temporal averaging thing immediately yields some performance gain of the algorithm. So we measured here the mean absolute error, the normalized mean absolute error, normalized by the maximum output of the PV plant. Secondly, we ask ourselves, what is the influence of the additional weather parameters? It's clear that the irradiation plays the main role when it comes to energy production of a PV plant, but there are also several parameters that are influencing the efficiency. So we took these additional parameters like temperature, humidity, air pressure, and the wind parameters like wind direction and wind speed, and trained the algorithm together with the GHI and these additional parameters. Furthermore, we provided also the algorithm with the actual hour of the forecast. So the neural network before did not know the state of the time stamp. So we included that here. And you see, many of the parameters do not contribute a lot if we put them as a single value into the algorithm. It could be said that the wind parameter seems to be the most influential one. But combining all additional weather parameters further improves the performance, and it shows that using all of the parameter makes the most contribution of that. So it seems that each of the parameters somehow work well together, and the combination gains then more than a single value. And so, concluding my part of the talk, we could show that comparing these first try, so without temporal averaging and DHI values only, compared this first approach to with the optimized algorithm, the optimized input data structure, we could improve the performance of the algorithm by at least 30%. And there's not been a difference between alpine and urban plants. The urban plants gain a little bit more, to say they perform a little bit better if you look at the precise values, but the performance gain is more or less comparable. And as I just received an email, this has also been published in the EU PVSec proceedings just today. So if you want to have a look at more of results of that kind, please look at that proceedings paper, or of course ask me any question after Angela's talk, or write me an email. And so I thank you very much for your attention of my part, and I guess I can hand over the word to Angela directly. So
thank you very much, Horst.
You're welcome.
And congratulations on the publication. That's great to hear, of course. So I will share my screen with you. I hope everyone can see well. And thank you again, Horst, and thank you also to Professor Dr. Bosorg for the possibility to speak here. My name is Angela Krainer. I'm the CEO of VelaSolaris, and I would like to give the business perspective on the results that Horst just introduced, and answering the question, what is the added value of simulating energy systems? So I shortly give a portrait of the company I'm representing, VelaSolaris. Then I would like to emphasize the benefits of simulation along the life cycle of an energy system, and come to the conclusion what results, benefits we as a company see in this project we do together. So let me start with VelaSolaris. We're the Competence Center for Energy System Simulation. We were founded 2006 as a spin-off of the Institute of Solar Technique at Rapperswil. And our main offer or main purpose is really energy system simulation. So we develop and sell the software Polysun, which does a physical simulation. So it is used by engineers or as well in research and development when you want to simulate an energy system holistically and dynamically. That means really combining all available technologies, power, heating, cooling, and even electric mobility, and simulate the functionality of the system dynamically and physically. So that's really the core of our business. And as you can see, simulation, of course, is very important to us. And this I would like to emphasize a bit more, because as we see the market and our clients, simulation is really used differently along the life cycle of planning and operating an energy system. And this is important to know because simulation addresses different problems along the way. For example, in the very early project stage, if you want to make a concept for an energy system, the main answer simulation will give you is really what option is the best one when it comes down to plan an energy system. So, for example, the question, how large should my PV plant be? Should I combine it with battery? How is self-consumption addressed if I integrate electric mobility? This is really simulation at an early stage to choose the best option. And here, physical simulation, of course, is used. And then when it comes to planning, the chosen system is more and more optimized, more detailed. For example, here is when you define by simulation the number, the type, the layout of PV models. And of course, here also many changes can happen. The roof size, for example, can change. So you need to adapt the energy system and again find a robust solution at the lowest cost. So here again, simulation is used. And this is basically the field where we are very active. We don't see simulation so much used in construction, but of course, simulation helps our clients also in the construction phase to perform construction according to plan and identify performance gaps. Where it gets interesting is in operation, and this, of course, is mainly addressed by the machine learning algorithm Horst just introduced, because here simulation is really used to optimize the operation of the energy system with regards to self-consumption or even integrating real-time power prices. So for us as a company coming from the dynamic simulation of energy systems, mainly here in the feasibility and planning phase, the collaboration is really interesting for three aspects. So the first aspect, which is for us interesting to find out, is that we gain insight into the accuracy of machine learning models to predict PV energy yield, and then of course compare it with the physical simulation. In order to do, or as a result of doing this, we then can identify how the physical simulation of our software Polyson can be improved, for example, with regards to PV system losses. That can be soiling, snow degradation. So we could use or combine machine learning methods with the physical simulation. So that's, of course, an interesting field we would like to explore more. And also, the third part is the evaluation of the business potential, because we have the long-term PV yield simulation with our own software, Polyson. We have the short-term prediction for the next day with a machine learning algorithm. And of course, we have, with a system in operation, the actual measured data. And we can combine these three to identify, again, performance gaps and see if the system is really working at its best, as it should be. And we believe here is another business potential that we would like to explore more. So thank you again, Horst. This is from my side what I wanted to share. Thank you for this opportunity.